Okay, so today we're going to talk about the EM algorithm. And we'll look at it for Gaussian mixtures. Okay. So basically, what we're saying is that the observed data come from a mixture of normal distributions. Okay, so here's just a very simple one-dimensional example. Could be something like maybe we're looking at the heights of people. Okay, and we could say this is a mixture of two normal distributions. Okay, so one is male heights, which will follow a normal distribution, maybe with a mean of 70 inches and a standard deviation of 3 inches. Okay, and then we'll have female heights with a normal distribution of 64 inches and a standard deviation of 3 inches. Okay, and so we've got this and this or something. It's probably not quite accurate. All right, so this is 64, this is 70 or something like that. Okay, and then so the overall distribution would look like that's actually like if they had to scale to 1, it would probably look, I don't know, I can't draw. Okay, but you get the idea, right? Okay, so some mixture of this, right? This is the overall distribution. Or maybe it's more flat. I don't know, something like that. Okay. Okay, I'm just making this up. All right, and so so basically, if we draw data from here, can we apply labels to the data points? Okay. So we got male heights, female heights, and we want to know can we successfully cluster the data? Okay, so this is a one-dimensional example, a two-dimensional example. Let me, happy Friday, everybody. Yay. Friday of 9th week. Next week is 10th week. And then finals week, spring break, spring quarter. Graduation, we hope, for many of you, and then the rest of your life. Who knows? Oh, I'm supposed to promote the Masters of Applied Statistics, which is it's a new program offered by the Stats Department. So there's the regular Masters of Science, okay, and then there's the PhD, and then there's the Masters of Applied Statistics. And this is for those of you who decide to go into industry, and then you're like, oh, I want to learn more statistics to do something like this, okay? Then maybe you can work for a year or two or a few years, and then while you keep your job, you can attend kind of these night classes and earn your master's degree, okay? So the program is just starting up this fall. probably cohort sizes of around 25 students-ish. So maybe in a few years from now, if you feel like, oh, I want to go back and get more school, but I also like earning money, so I don't want to quit my job, Masters of Applied Statistics might be a good option if you're still in the LA area, okay? So anyway, and I'll be teaching there also. I'll be teaching I think the first class that you would take. So that you might even, because you're undergrad stats majors, you might get credit for it and say like, you don't have to take my class, but it could be fun. All right. Okay, so this is what we've got going on. Can we successfully cluster the data? A two-dimensional example, and you could just imagine the higher versions, like just picture it in your head, right? So 2D, you'd have a multivariate normal distribution. So that would be normal with mean mu as a matrix and sigma, right? And these come from, your x sub i's come from this. You got one mixture or a possible other mixture, something like this, okay? And you'd have mixture 1 and maybe mixture 2. Something like that, okay? So you have this kind of mixture of normal distributions. Can we appropriately cluster these, okay? Okay, so this is kind of, there's going to be just writing a bunch of gibberish up here. Not really. It's important stuff, but we got to get through kind of the math here. All right. So we've got we'll say we have some data set D defined as our observations x1 through x sub n. Okay, and these are each x sub I is kind of a d-dimensional vector observation. So basically, if you have a two-dimensional thing, you're going to have two values for each x observation, right? That makes sense, okay? And they're coming from some kind of they come from a mixture of components. Okay. And so basically what it is that the probability of any particular value x given some set of thetas. This is kind of our parameters of our model. This is a mixture of k components, okay? And so what we have is okay, so this is P sub k basically is kind of the this would be the kind of the normal would be our normal distribution, right? For component k. Okay, and then this z sub k, the z, okay, is a vector of group membership. So if if you've got 3 components, so for example 3 components, you would have basically a 0, 0, 1, 0 if it's in the second component. Okay, and then alpha sub k, this is our these are the mixture weights. So here, basically, we would say, maybe you know that component 1 is much larger than component 2 or 3 or something like that. Basically, the different components can have different probabilities. Okay, mixture weights. So basically, larger components will have heavier weights. Okay, but if you add up all of the weights, so if you add up all the weights, what do we get? Basically 1. Okay, so if the first component consists of 50% of your data, your alpha for that weight is 0.5. Okay, and so basically this just says, okay, multiply the weight times the probability of being times the probability of getting this data point under this model, and then add them up. Okay. All right, is that okay? And so, so for example, let's say we have a mixture like this, okay? That's no good. Why am I having such a hard time? Okay, so we can look at, like, we've got 2 components. This will be component 1. And this will be k equal to 2, right? So if you get a data point, so if this is a data point 1, so x of 1, we would get the probability of x of 1 given our thetas. This would be, we would look at, maybe this one's larger, so alpha sub 1 maybe is 70%, and alpha sub 2 would then be 30%, right? So effectively, when we look at this, this is kind of we would mix 70% times what's the probability of being in component 1, right? So basically, what's the density here? It's practically 0, right? So the probability of getting x1 from component 1, this is kind of on the order of 0, right? Because if we're out here, component 1, this is, we're like 5 standard deviations from the mean. So this is like close to 1, and then we would add up kind of 0.3 times what's the probability? It's quite high, maybe not as high as being over here or whatever, but this is on the order of like 0.2 or something, right? This is kind of the density of probability kind of x1 given kind of the parameters, the mean and standard deviation for component 2. Does that make sense? Okay. Whereas if we get a data point here, we realize, okay, it's there's a mixture between component 1 and component 2. Does this kind of make sense? So we're taking into account kind of the density, the value of the density at that point, but also the weights, the relative likelihood of being in this group or that group. Okay? And so our weights I'll call this the membership weights can be thought of as such. Okay, so the weight of observation I being in group K. Okay, so this is kind of the weight of observation I being in group K. So this is basically, you know, the probability so, you know, think of Z as kind of that vector of zeros and ones. You know, if we're talking about observation I, what's the probability that the kth element for Z sub I is equal to 1? Okay, and we're going to calculate this given our x sub I value and our current set of theta parameters. Okay, so this is the probability that the kth element in the Z vector for observation I. Okay, given the observation x sub I, and parameters theta. Does that make sense? Okay, and so basically, all we're going to do is we're going to take kind of the total probabilities, and then we're going to say the probability of being in component 1 is going to be this portion divided by the total probability, and then the probability of being in component 2 will be this portion divided by the total probability, right? So we could think of this as kind of the total probability-ish, okay? Kind of the total probability of observation I, okay? And then it's just going to be, you know, what's the probability of being in component 1? It's going to be, well, the portion that's because of component 1 divided by the total probability, and then the portion being in component 2 divided by the total probability. So what would we get? We would say the probability for being in component 1 is close to 0 because this thing is going to be 0. And then that means the probability of being in component 2 is going to be close to 1. See, in my head, I feel like I'm making sense, but then I'm looking at you guys and I'm not sure if it's coming through. So I'm going to write this. Okay, I'm going to write kind of the correct formula notation for this, and I'll try to explain. So basically, we're just going to say, okay, what's the probability of being for component K of getting observation x sub I? Okay, and this basically says times given theta k times alpha sub k. So the numerator is, you know, the probability of our observation the probability of getting our observation in component K times alpha times the weight. Okay. So that goes in the numerator, And then in the denominator, it's just going to be this value summed across all of the components. Okay, so you just calculate this thing, and you do it for all of the components. So it's going to be, it's going to be ugly. Okay, so because to indicate that you're going to do this for all of the different components, we use a different letter M, and it's going to be x sub I given z sub m and theta m times alpha sub m. Okay, but basically just do this thing for all the components and add them up. Okay, so basically, essentially you calculate the same thing as the numerator, but for the different components. But for all the components. Okay, and so now we get a probabilistic thing of weights. Okay, so what we would get here is kind of our total probability here would end up being kind of like 0 plus 0.06 or whatever. Okay. And so this is effectively kind of like our denominator. Okay? And then the weights for the components, the resulting weight vector, would then be, we would do 0 divided, our total is, 0.06. So for the weight for the first element would be practically 0. And then we would do 0.06 divided by 0.06, and then the weight for the second component would be 1. Okay, so our weight for this point would be something like 0, 1, because when we look at it, it's much more likely to be in component 2. Okay, so this is just a probabilistic version of assigning components. Okay, and whereas if we got an observation here, we would say, okay, we look at the density over here and we say it's much higher, and we look at the density over here and it's lower. So already it's favoring component 1, and on top of that, we look at its relative weight and we see that it's already heavier over here, and so it favors component 1 even more. Okay, but it's not a 0 probability for being in component 2. So this might be like probability, the weight for component 1 maybe 0.8, and the weight for component 2, 0.2. I'm just making those numbers up, okay? But you're getting a probabilistic version of assigning components. And that's what we're doing with membership weights. Is that feeling all right with you guys? Kinda? Okay. If we compare this to k-means clustering, basically, k-means clustering, we're doing something similar, except it's not a probabilistic association of classes, right? So here we are saying there's like an 80% chance it's in component 1 and a 20% chance of being component 2. With k-means clustering, we're just saying which component center is closer, that's the one you're in, okay? So that one is you're either in this component or you're not. We're not doing any kind of probabilistic assignments, okay? With the EM algorithm for mixture models, we are giving probabilistic class assignments. Okay, so just with the EM algorithm, component assignments probabilistic. Okay, so it's like 0.8 probability of component 1, 0.2 probability of component 2. And the probabilities of the components depend on the component's parameters, right? The mean and standard deviation of each component, multiplied by its kind of initial, multiplied by the weights, the relative weights of those components, okay? So, so here, these component probabilities depend on basically your x and the component parameters mu and sigma, okay, along with the component, what do we call these? Are they also called weights? Yeah, the component mixture weights, alpha. Okay, you know, versus k-means clustering, component assignments are not probabilistic. Okay, we just looked at the center of each component. The centers of the components. Whichever center is closer, the data point gets assigned to that component. Okay, so that is it's kind of a contrast between how this assignment works and versus k-means clustering. Okay, so let's talk about the EM algorithm, okay? So with the EM algorithm, there's basically two maximizing steps. Okay, so the, whoa. Okay, so we have the E step. All right, and so we take our current values, our current, or, you know, possibly initial, values of theta, okay? So theta being the mean and standard deviation of the normal distributions, okay? And then we calculate all of the W sub I k weights. Okay, so we will end up getting n by k matrix, right? So W sub I k is going to be n by k matrix, you know, basically one row per observation and one column per component. Okay, and each row adds to 1, okay? Because all of the different weights will add up to 1. Okay, so if we have two components, maybe 0.8, 0.2. This says 0.8 probability of being in component 1, 0.2 probability of being in component 2. Okay, and it could be like 0.00001 and 0.99999 or something like that. Okay, so that means it's very likely to be in component 2, very unlikely to be in component 1, or something like that. Okay, so we calculate this for all of this. Okay, so this is our E step. So we calculate kind of the weights, the class membership based on our current values of theta. Okay. All right, and then the M step, okay, is now that we have our weights, we're going to update our parameters theta and also our alpha to maximize the probability of our things. Okay. So basically, given the component weights, or given the weights of the components for each observation, we will update all of our parameters to kind of to maximize our data likelihood. Okay, so our parameters, we've got the mixing component parameters. We have the means of each component. And we basically the variance or the standard deviation of our kind of our this is if it's multi-dimensional, it'd be like our variance covariance matrix, our variance matrix of each component. Okay. All right, well, how do we do this? Well, this has been kind of solved for us, so we can benefit from other people's work. If we had to derive them ourselves, we could do it. So so at the next, so for the next iteration, okay, alpha, so I guess our new alpha sub k will be equal to n sub k divided by n. Okay, n sub k, so is basically n sub k is effectively the column total. Okay, so whoops. So, wait, where did, shoot. This is not what I want. Okay, so we get our weight column. Effectively, we're going to just take, so each row adds up to 1, but what we're going to do is we're going to take the column total, and this is effectively the number of data points that have been assigned to component 1. And if we take the column total over here, this is effectively kind of like the number of components that have been assigned to component 2. Okay, and that kind of makes sense, right? They're not necessarily ones and zeros, but they're probabilistic weights. But we can kind of treat them as like, if we add them up, we're going to get the kind of the number of data points assigned to component 1. Okay, so n sub k is effectively the column total of the WIK matrix for component K. So this is like the number of values, number of data points assigned to component K. Okay, so this becomes our new mixture weight. Okay, so we do this for all of the components. Okay, and then our new set of means is going to be effectively we take the weight of our weight matrix and we multiply it by our x data points, okay? And we sum this up for all of our data points, okay? And then we're going to divide by how many data points are assigned to component K. Okay, so this is kind of like just the weighted mean of all of our data points, right? So this is effectively weighted mean of all our data points. Okay, so you know when you calculate the mean of something, you just add up all of the data points x and you divide by n, right? So the regular old mean would just be, you know, versus the usual mean, which is 1 over n times the sum of x, okay? So it's pretty much the same thing. We're just throwing in a weighted term so that the values that are very likely to be in component K, those are the values that count. The values that are unlikely to be in component K, those ones hardly count towards the regular mean value. Okay, so we use that. Okay, and if also the standard deviation term, okay, for each component K is quite similar to how we would calculate the variance, right? So effectively, you're going to do x sub I minus mu, okay? So x sub I minus mu sub k. So once you figure out these mean terms, you're going to do x sub I minus mu sub k times x sub I minus mu sub k transpose. Okay? So this effectively gives you your, your variance covariance matrix. And then what do? You weight them all, okay? You multiply your weight matrix by this so that the variance and covariance terms that should count, and the ones that shouldn't count don't count, and then you add these all up and you divide by how many value points you have. Okay, so if you compare the way you would calculate your usual mean and your usual variance terms, okay, so this is kind of like the weighted variance matrix. If you figure that out, versus the usual would be kind of like a 1 sub n, or for like the maximum likelihood, x minus mu transpose. It's very similar. All we're doing is we're just weighting these, okay? And so we we have a mixture of components. We have to figure out our weight matrix based on our current parameter values. Once we get this weight matrix, then we go back and we try to update all of our parameter values based on kind of these weight assignments. And then we just iterate back and forth, okay, until we reach some kind of convergence. And this would work as well, okay? I hope it makes sense. Okay, that's it. That's all we got. Have a great weekend, you guys. Hope the homework goes okay. I guess next week we can start looking at See, I want to do some coding, but I also want to assign some of the coding to you guys in the final. So maybe we'll try to think of stuff.